Hello, everyone. My name is Cheng-Chien Chen. I'm from Department of Physics at the UAB. I'm also involved as a senior personnel in the Center for Additively Manufactured Complex Systems under Extremes. This DOE center led by Professor Yukishi Vora, also at UAB. So today I'm going to discuss computational materials modeling using first principle calculations and the machine learning simulations. So this is an outline of my talk. So today I'll first introduce superhard materials. So this will serve as an example systems where we apply our computational methods. And of course, we can also model other mechanical properties as well. And then I'll give an introduction to the methods we use based on first principle calculations and the machine learning simulations. Now I introduce two specific systems. First is a superhard materials based on BCNO compounds. In particular, I'll discuss our evolutionary structural searches and active machine learning for discovering new ternary BCN and BNO superhard materials. And then I'll discuss high-entropy ceramics, especially on the high-entropy borides. I'll discuss our simulation for the synthesizability of single-phase high-entropy materials, the simulation of the mechanical properties, including the use of random forest machine learning methods. And finally, I'll conclude with some future and ongoing research directions, especially on simulating finite temperature properties with molecular dynamics simulations. Okay, so to begin with, superhard materials have many applications such as a drill or cutting tools, or serve as a protective coatings, thereby useful for extreme environment applications. And one way to define the hardness of a materials is through an indentation test. For example, you can use a diamond tip to hit a material surface, and from the applied force and the resulting areas, one can define a hardness which is proportional to the force divided by area. So thereby hardness has also a unit of pressure. At ambient condition, cubic diamond is the non-hardest materials with a hardness about 100 GPa. But its application can be more limited because of size and cost, and also its performance can degrade under high temperature or humid environments. Other possible superhard materials include, for example, cubic bond nitrides, with hardness about 60 GPa. The crystal structure is known here. And nowadays we define a material to be super hard when the hardness value is larger than 40 GPa. Okay, so this chart shows the hardness values for two major classes of materials. So the first is based on light elements, boron, carbon, nitrogen, and oxygens. So these materials, they can form short covalent bonds and thereby very strong structures. So this includes diamond, cubic nitrides, and other BCNO materials. Another class of superhard materials is based on transition metal borides or carbides, such as radium diborides, osmium diborides, etc. And there are advantages and disadvantages for both classes of materials. For example, we know in the light elements, BCNO, they usually show higher hardness values, and their raw materials are cheaper relatively. Wowever, the problem is that these materials usually require high temperature, high pressure synthesis. Okay, so large scale production will be a challenge. For the transition metal borides or carbides, the advantage is that they can more easily synthesize at ambient conditions, thereby to facilitate large scale production. And the hardness value are sometimes smaller, less than 40 GPa. Also, the raw materials can be more expensive, especially for the transition metals. And now, for both families, their binary material compounds have been extensively studied in the literature. So nowadays, the future directions, for example, for BCNO is to look for new ternary or even quaternary BCNO compounds. And for the transition metal borate or carbides, the idea is to study what is called high entropy materials, consisting of 5 or more elements. Okay, so this we'll discuss later in this talk. So next, I want to talk about our simulation methods for modeling the properties, especially the mechanical property of these systems. Okay, so I first want to discuss the concept of multi-scale modeling. Okay? So as an example, if you want to model the properties of, say, asphalt, okay, then depending on the scale, you will want to use different methods. For example, if you are talking about a macro or human scale, then usually you use some kind of continuum methods or coarse-grained finite elements methods. However, if we are talking about how the constituent atoms affect the physical properties at the microscopic or atomic levels, then often you will use quantum mechanical simulations based on, for example, density functional theory, or at the mesoscopic scale based on molecular dynamics simulations. Okay, and in this talk, we are mostly interested in what we call intrinsic properties at the microscopic level. So we are relying heavily on density functional theory simulations. Okay, so for density functional theory, DFT, so what we need is an input crystal structures that's close to the experimental structure. And then once we have the structural information, we proceed to solve basically a couple of a single particle Schrödinger equations in a self-consistent way. And after we obtain the solution, then we can obtain basically the total energy or stress relations, and thereby also the elastic constants. And for the calculation I'll be showing, we are using the plane wave shooter potential DFT codes based on this popular VASP and the quantum espresso softwares. So usually for given crystal structures, we will check a few stability criteria. First of all, is the thermodynamic stability. This means that for the Gibbs free energy, which consists of the enthalpy and the entropy term, we want to make sure that this Gibbs free energy is at least in a local or global minimum, corresponding to metastable or stable states. And sometimes we also check the mechanical stability. Okay, this means that we want to make sure in the elastic constant tensor, the eigenvalues they are positive. And finally, we can also check dynamical stability. This means that, for example, in the phonon spectrum shown here, we want to ensure that they have only positive phonon modes. Okay, so as a quick example, here I'm showing a previous collaboration with Professor Yogi Shivora and Professor Aaron Catledge's group at the UAB on studying a superhard B50C2 compound. That is corresponding as EN image. And on the right-hand side, I show two possible crystal structures. Okay, so they have basically a boron 12 icosahedrons, and together with extra boron and the carbon atoms lying at the high symmetry Wyckoff positions of this crystal. And in the bottom structures, we have some carbon atom replacing one of the boron atom in the boron 12 icosahedron. Okay. And the right-hand side, the corresponding theoretical simulation of the phonon spectrum, you can see here we have imaginary phonon modes, while in the bottom structure, all the phonon modes are positive. Okay, so this is an indication that the bottom structure might be dynamically more stable compared to the above one. Also provide some additional suggestion guidance for the experiments. Okay, so this is the case when we know the crystal structures. However, sometimes we have only the chemical composition information, but we don't know actually the structures either from theory or in experiment. Okay, so in that case, we need an extra step of crystal structure prediction. So for crystal structure predictions, this means that we only specify the chemical formula and the possibly also the number of atoms in the unit cell, and we try to find the local minimum of the Gibbs free energy. And these entropy terms are sometimes complicated to model. So for this purpose, quite often in the literature, people are trying to minimize the entropy. Okay, so right hand side is a schematic cartoon showing the potential energy surface. And usually is this crystal structure prediction is an NP-hard problem, so you have very complicated surface with a lot of local minimum in addition to the global minimum. Okay, so to localize the minimum positions, you need a very powerful optimization techniques. Okay, so one of the methods we have been using is so-called evolutionary searches. So this is based on the biological concept that, so for example, you can from parent crystal structures, you can be combined through heredity apparatus to form child structures. And this child structure can undergo further, for example, mutation apparatus, such as lattice distortion or atomic displacements. And we can evaluate the energy of the child structures. And if they have lower formation enthalpy, then they'll be decapped and become the parent structures for the next generation. And one keeps iterating this process until the results converge. Okay. And here we are using a powerful software, USPEX. There are also several other software of similar capabilities. On the right-hand side, I'm showing this example, again, a collaboration with Professor Yogeshwara's group on studying a superhard BC5 compound. And here, as a function of the number of generation in the evolutionary searches, we see that the enthalpy becomes lower and lower. And at roughly 40-ish generations, the calculation converges to orthorhombic BC5 structures. And we also further compute the harness value of these structures, come out to be roughly 60 GPa, again, in good agreement with the experiments. Okay, so the DFT calculations and also these structure searches we just discussed can be computationally expensive, especially when the unit cell has lots of the atoms. Okay, so therefore we to facilitate large-scale computational materials modeling, it'd be nice to have alternative methods, and one of very promising one is of course machine learning. So nowadays we have heard about a lot of buzzwords on machine learning. So here let's focus on the most popular machine learning task, which is called the supervised learning. Okay, in this case, you are provided with some input features A, and our goal is to predict some output or target property we call B. Okay, for example, if I give you the a location and condition of house, and you want to predict the housing price. Okay. So what we need to do is we need to prepare collect training data sets with different samples and their corresponding features, and also their corresponding target value we want to predict. And quite often we call this feature matrix X. It's a consistent of the feature vectors, and the target property to predict, we call it a vector Y. So once you have this, we can start to you can pick your favorite machine learning models to train the model and eventually to make predictions. Okay, and one of the simplest model is called the linear regression. Okay, so this is simple. So this target property is simply a linear superposition of the input features and with different weights, W0, W1, W2, etc. Okay, and the machine learning task will learn these weights based on our existing samples. And once the weights are learned, we are able to make a prediction with this model. An example I show here is the housing price. For example, these are actual data, housing price versus the distance of a house to the nearby mass rapid transportation. Okay, and we might expect the housing price will be kind of inversely proportional to the distance to the nearest train station. Okay, in this case, you can train a linear model shown as this red dashed line. And once the model is trained, you get the corresponding weights. We can make a prediction quickly. And of course, if you have multiple features, then you will train a linear regression model with multiple variable. This is called multivariate linear regression. So although this is a fairly simple model, so of course the accuracy can be more limited. However, the model has an advantage that it's very easy to train, and it provides you the intuition about how to interpret your results based on the weight of the corresponding features. Okay, and in fact, this linear regression also play a very important role in the more advanced machine learning model like artificial neural network for deep learning simulations. Okay. So here I'm showing a very simple neural network architecture. Okay, so basically we have something called input layers. These are basically our feature vectors, and you can multiply these input features with some corresponding weights and provide it to our hidden layer. Okay, so what our hidden layer will do is to make a nonlinear transformation through a so-called activation function, and this function can be, for example, sigmoid, tanh, or ReLU, as shown on the right-hand side. Okay, so the main point is to introduce some kind of nonlinearity to the system. And finally, after this nonlinear transformation, we can then make an output prediction. Okay, so this is one of the simplest artificial neural network architecture, and you can see this linear regression plays an important role here. Okay. And of course, from this we can construct even more complicated deep neural networks. Okay, in this case, you will have multiple layers and we have multiple neurons, and the output of each neurons can become the input for the neurons in the next layer. Okay, from the so-called fully connected feed-forward neural networks. Okay, and this sometimes also known as multi-layer perceptron. Okay, and this quite often is already very powerful machine learning task for materials discovery. So another type of machine learning methods I will be discussing is based on so-called decision tree. Okay. So this is just an example of feature matrix and the corresponding target vectors. Okay, so we don't need to be concerned about the details of what this each feature or target mean. Okay, but basically once we have the feature matrix and the target vectors, so decision tree will proceed by asking questions based on these features, and then split our training samples into different subsets. Okay, and one can then ask further questions on the subset to further split the data set. Okay, eventually you will form a tree-like node leaf structures. Okay, so that's called decision tree. So one problem with decision tree is that it can be quite often it will be overfitted. Okay, so this means that the model will perform very well on your training sets. However, its generalizability to new data sets is very poor. Okay, so we have to keep in mind that in machine learning simulations, our major goal is to make predictions on new data never seen by our model. Okay, so if you have a model works very well for only on the training data set, it's not very helpful. Okay, so one way to tackle this overfitting problem is to consider ensemble methods. Okay, for example, in random forests, you basically consider a lot of decision trees and then you average the results, so that will help reduce the overfitting problem. Another way is to consider so-called gradient boosted trees, where you build one tree at a time, and for each tree you will improve the weak points from the previous tree sequentially. Okay, and in fact, this gradient boosted tree is very powerful, and it's often the championship model for winning several Keiko data science competitions. So one thing important to pay attention to is that when you choose your model, you have to the data size of your training sample set is also a very important factor to consider. Okay, for example, this schematic diagram shows the model performance versus data size. Okay, so for different models, of course, we expect the larger the data set, the better the performance as we expect. However, we have to be careful that when the data set is small, sometimes the traditional machine learning models like decision tree, like random forest or gradient boosted trees can outperform a more complicated neural net model, neural net models, because of this model has many parameters to tune, and if your data set is too small, you can easily run into overfitting problems. Okay, so this is especially important for our materials and science and physics problems, because quite often our data sets we can get on the order of 10 to the 3 or 10 to the 4th. Okay, so in that cases, a transition model might be sufficient. Okay, this is unlike the case of, for example, image recognition problems in computer science. We can easily get say 1 million pictures on the internet. Okay? And for large language models, for example, like a ChatGPT, so they are usually trained with training samples on the order of 1 billion or even to 1 trillion. Okay, so this figure is important one for us to keep in mind. Okay. All right. So after this introduction, okay, yeah, another thing important I want to discuss is about the features. Okay, so the question is, what kind of features do you want to use? Let's say, for example, we want to predict the electronic band gap, e.g., for materials. Okay, and then we know, for example, for binary oxides, it is known that the band gap is proportional to the square of the difference in the electronegativity between the two elements. This means that if you can come up with if you can compute the electronegativity difference for a binary material, then you can fairly accurately predict the electronic band gap. But also we know that the band gap is, I say, inversely proportional to the square root of the dielectric constant. Okay, so if you know the dielectric constant of materials, you can also fairly accurately predict the band gap. Okay, so the questions will, of course, and we know now the electronegativity difference and the dielectric constant, they are not independent, they're correlated, because they are also correlated with the electronic band gap. So the question is, which features do we want to use? Okay, and we know, for example, if I give you a compound, I know the chemical compositions, then we can very easily compute the corresponding electronegativity difference. However, for even for non-material, I may not know the dielectric constant, and even for and also for new materials, we will not be able to know the electric constant unless you do extra calculations or further experiment. Okay, so this thereby prevents us from large-scale materials screening. Okay, so in that case, these features based on only the chemical formula would be preferred. Okay, so here I'm showing a 2022 paper from MIT group. So what they have done is they train different machine learning models to predict different quantities. For example, formation energy, electron band gap, bulk shear moduli, and the density, etc. Okay, so what they have trained different models with different features. Okay, for example, the blue ones shows the model trained with only the compositional features. So these are the features you can derive directly from the chemical formula. And this red one are model trained with using compositional features with additional structural information. And obviously, we expect the this model to be more accurate. So you can see from the mean absolute error. So these red models have a lower error, okay, because now we have additional information. Okay. However, one thing to notice that even for models without structural information, the performance is already quite decent. Okay, actually, in some cases, the performance is already very comparable to the models trained with structural information. Okay? And as mentioned, if you have a new materials, sometimes we may not know the structures. Okay, so thereby, if possible, we can use only the compositional features only to facilitate large scale calculations. Okay, so with these introductions, I'm now ready to discuss some of the applications. So first of all, this is the 2021 paper published from my group on MPJ computational materials, where we apply this workflow we just discussed to discover new superhard ternary BCN system. Okay, so for machine learning applications, the first step is to acquire data, right? So what we have utilized is the material project database, consists of lots of computational the structures and the material properties for a variety of crystalline materials. And from this information, we can generate corresponding features, and where we use only the compositional features to facilitate large-scale applications. And once we have the input data, the target value, and the features, we can train our ensemble tree models with the scikit-learn packages. Okay, and once the model is trained, we can apply it to study BCN superhard materials with varying compositions. Okay, and once we have the promising superhard compositions, we did not stop here. We then perform a crystal structure prediction using the USPEC software to come up with the possible crystal structures. And once we have the structures, we then perform DFT simulations with VASP to compute the electronic properties and the material properties to validate the results. Okay. So this is the overall workflow, and in general, apply to a lot of different machine learning problems for material science and physics. So here in the end, this histogram plot show the distribution for our training samples. The blue are for the bulk modules, orange for the shear modules, and we have in total about 10,000 compounds we selected from down select from materials project database. Right side similar plot, but now a scatter plot for shear and the bulk modulite, and also the force color intensity represent the hardness value. Okay. I want to notice that on the materials project, we have only information from the bulk and shear moduli. Okay. However, we can use some kind of empirical model, for example, from this TENS model, where we use the K is the force ratio, is the ratio between the bulk and the shear and the bulk moduli, and G is the shear moduli. We can compute the corresponding hardness values. It's shown here. Okay. So here our goal is to find superhard materials between above 40 gigapascal. Okay, so this is our results of our random forest models. So what I'm plotting on the vertical axis are the density function theory calculation, say on the bulk, shear, and the hardness values. And this we are considered as the ground truth. Okay. On the horizontal lines, these are the predicted machine learning values. So in training the model, we use 60 features based on properties that can be derived from the chemical formula, as I just discussed. And we split our 10,000 data sets into a 90% training set and a 10% test set. Okay. So the result we eventually, in the end, we evaluate results on the test sets, which has never been seen by our models. And there are different ways to evaluate the performance of a machine learning model. Okay. One possible way is to look at the Pearson correlation coefficient between the predicted value and the actual value. Okay, so this Pearson correlation coefficient will basically measuring the linear relationship between the two quantities. For example, if the prediction is 100% accurate, then all the points will fall on this red diagonal line. Okay, of course you see there's some deviations, but overall we can achieve a 0.94 correlation between the bulk modulus between the prediction, which is already pretty decent. Okay. For the hardness models, performance is worse. It's understood because, as I mentioned, this hardness first person data actually obtained through a empirical models based on the bulk and shear moduli. Okay, so we expect larger error. However, even though we can still it can still capture the overall trends, and which is enough for us to make some large scale prediction. All right, okay, so we then apply the resulting machine learning model to construct the so-called ternary graph for BCN compositions, and we can give arbitrary compositions, and the model will tell you the hardness and other bulk and shear modulus information. And by the way, we have published our Python machine learning course on GitHub, and you can check this paper for further information about how to download the software. So let's focus on the hardness value. Okay, so the result shows that if along this region you have some superhard compounds, this means that if you have a material with a boron nitrogen ratio 1:1, is likely to have a super hard composition. Okay? And also close to the corner of diamond, you can also get super hard materials. Okay. So based on these results, we have identified 3 new ternary BCN compounds: BC10N, B4C5N3, and B2C3N. So they have predicted machine learning hardness above 40 GPa. So that question is, how do we know the results are reliable? Okay, so that's why we perform extra evolutionary crystal structure predictions, and these are the resulting structures. And in the middle, there are corresponding phonon dispersion relations for these structures, and you see that all have only positive phonon modes, so this structure dynamically stable. Right side are the electronic band structures. So the BC10N is a wide bandgap insulator, and the B4C5N3 is in super hard metals with finite density state across the Fermi level. Okay, so they both have a formation energy above about 0.1 electron volt above the ground states. Okay, so they are metastable structures. However, this does not mean that they cannot be synthesized. Because an example would be, we know cubic diamond is also metastable structures in ambient conditions, but it can be synthesized at a high pressure condition. So this is interesting paper from 2018 Science Advance. So the authors have listed a bunch of different compounds and their corresponding formation energy above the ground state. Okay, and these gray bars indicate to what extent these theoretical compounds can actually be synthesized. Okay, and you see roughly between 0.1 to 0.2 electron volts per atoms above the ground state for the formation energy, that's still possible to be synthesized. Okay. So this means that there's a chance that this our really predict super hard compounds can be synthesized. I want to point out, once this BC10N is synthesized, there's a theoretical hardness value above 80 gigapascal. So once synthesized, this could become the second non-hardness material just next to diamond. Okay, and so after our success with BCN, we then want to proceed to discover new BNO compounds. Okay, so these I expect to perform well under oxidizing environments. So the challenge here is that in the literature, there are very few BNO materials. Okay, so in fact, if we apply our general machine learning model to predict the hardness value of these systems, we get about a 50% error. Okay, so we have a large error. Okay. So therefore, we choose a different strategy. Okay, so based on so-called active machine learning. Okay, so in this case, we generate our own BNO data from first principles and train machine learning model, and use the resulting model to guide our selection of the compositional for the compositions, and perform additional first principle calculations, and then update the machine learning model. And you keep iterate this procedure until the results converge. Okay, so this is called active machine learning. So this is an example on the top left on the ternary graph. This green and red dots indicates the compositional feature, the compositions we consider for first principle calculations. Okay, so these green ones means they are elastic stable structures. The red one means they are elastic unstable structures in evolutionary structure searches. Okay. So based on these samples, we then construct a corresponding machine learning model based on random forests to predict the cohesive energy. Okay, so it's like the opposite of formation energy. So here we want the higher the cohesive energy, the more stable the compound is. And one can see in this region, for example, we have a high cohesive energy, they are more stable. Okay, so then based on these machine learning results, we can focus on regions that are potentially more stable and can perform additional first principle evolutionary searches. And from these results, we then train the second iteration of machine learning models, and we keep iterate this process. Already at the fourth iteration, we see the results kind of already converge. Okay. So we use this method to construct corresponding random forest model to predict the cohesive energy, the density, and the hardness value. Okay, And in all cases, you can see, although we have a very small amount of data sets, we achieve fairly high Pearson correlation coefficients on the test set for the actual DFT value compared to the predicted value. So let's focus on. So first of all, we see there's a region where with high cohesive energy means that the composition will be more stable, and also there's a region around this boron nitride 1-to-1 ratio where they show high superhardness. Okay. In fact, we have identified a chemical composition of Bx+2 and XO3. So this would be along this region of high cohesive energy, so they're stable, and meanwhile with potential high hardness. Okay. So as an example, we consider B5N3O3, B6N4O3, B7N5O3. So they are corresponding crystal structure from evolutionary researches. The electron dots showing that they are all wide bandgap insulators, so they are stable. Okay, so the ferron dots all positive, so they're also dynamically stable. Importantly, they have hardness value all above 40 GPa. Okay, so they are all potential superhard BNO superhard insulators, and that can potentially be synthesized in the future. Okay, so now in principle, we can continue this computational workflow and strategy to discover higher order materials, for example, a quaternary BCNO compound. Okay. However, there will be another challenge. Okay. So so this paper in 2019, MPG computation materials. So where the author have utilized the A-flow materials database. So they compute the corresponding enthalpy gain by forming, for example, higher order compounds using the corresponding binary or ternary or mononary materials. Okay. And what they found is that the entropy gain you had when going to higher order, especially above quaternary compounds, becomes almost zero. Okay. And in these cases, the enthalpy terms will become dominant. Okay. So this is the reason why if you want to use the workflow to study quaternary or higher order compounds, you will have to probably like to consider also the entropy effects. Okay. So this then leads to my next topic about high entropy materials. Okay. So so these high entropy materials are basically formed by 5 or more elements in a roughly equal molar compositions. Okay, and we know that if you mix different atomic elements together, so there are a few possibilities, right? For example, one possibility is that they will phase separate and form regions of different elements. Okay, in this case, this will be a multi-phase compound. Okay. Another possibility is that these different elements, they can uniformly, randomly distribute throughout the lattice, forming a uniform single phase solid solution. Okay. Of course, this the result will be dependent on the competition between the enthalpy term and the entropy term. Okay. And for entropy materials, you have an entropy gain related to the gas constant R times the log of the number of elements you have in your system. Okay. So the more the elements you have, the larger the entropy gain. Okay, so it's more likely you can form a single phase solid solution. So why do we care about these high entropy materials? Okay, so here I'm showing a scatter plot for as function of the fracture toughness and the yield strength for different families of materials. And this red region are these are common metals and alloys. So they usually have one major base materials, for example, copper or aluminum, and with addition of a small ratio of secondary elements. Okay. However, for high entropy materials, for example, high entropy alloy, chromium, manganese, iron, cobalt, nickel. So they have 5 or more elements in roughly equal molar ratios, and you can see that they sometimes they can show superior mechanical properties compared to this their binary or ternary counterparts. Okay, so the first high-entropy materials were synthesized in 2004, especially reported in these two papers by Jingwei Ye and Kenter. And nowadays, later people have extended the concept to form also so-called high-entropy ceramics. Okay. So two system we want to focus here is the cubic rock salt structures of the cubic carbides, and also the hexagonal AlB2 structure of entropy borides. Okay, so in this case, for example, one will use AlB2 hexagonal structures, but now replace the aluminum atoms by five, for example, by 5 different transition metals for 5 metal high entropy borides. So in the study of these high entropy materials, there are two key questions to ask in theory. So first of all, how do we model the synthesizability of single phase solid solution of this material? Okay, for example, we just discussed if you mix the elements together, it's not guaranteed that they will form a single phase. Okay, same time they can be separated and form multiple phase material. So how do we model the synthesizability? Okay. Second question is if the material is formed, how do we model their mechanical properties, especially how to treat the LOE disorder effect? Okay, so there are two commonly used first principle methods. One is based on so-called the special quasi-random structures, SQS. Okay, so basically this is basically a big supercell, and try to with a fixed amount of atoms in the unit cell, and try to mimic a perfectly random infinite crystal, which can be known analytically in the thermodynamic limit. So this is an example of a big SQL supercell used in DFT calculations. Another method is called the partial occupation, okay, POCC. Okay, so in this case, one asks the questions. So how do we consider a small unit cell, and then with different shape and geometry, and to tile the desired crystal symmetry in the infinite space? Okay, so this is how POCC works. And when the both cells are big enough, the two methods will basically coincide. However, in practice, for SQS, one wants to consider the largest possible supercell you can have in your calculations. And for POCC, one wants to consider the smallest possible supercell that's compatible with the underlying stoichiometry. Okay, so we'll be discussing both methods. So first of all, for the POCC, it has an advantage that it can help to compute the synthesizability. Okay, so this is based on the paper 2018 Nature Communication paper from Professor Kutororo's group at Duke University, where they consider 5 metal cubic carbides. Okay, for example, in this formula. Okay, so to be compatible with the stoichiometry, one need to consider a minimum 10 unit cell. Okay, in this case, we have 5 different transition metals and 5 carbon atoms. Okay, and then you then consider different partial occupation POCC structures that can tile up the space with a cubic symmetry. Okay, so in total, they found there are 49 distinct POCC structures, and then they proceed by consider 56 different compositions by choosing 8 different refractory metals. So 8 choose 5 equal to 56. Okay, so the calculation proceeds by for given chemical compositions, we compute the formation enthalpy for all 49 distinct POCC structures, and from the resulting distribution, the width of distribution in the enthalpy, you can define the EFA value, which is like the inverse of the distribution. Okay, so here the definition G is the degeneracy number for each structures. HI is the corresponding formation enthalpy. Okay, so but basically, the wider the solution, the wider the distribution, the smaller the EFA value. The higher the the narrower the distribution, the higher the EFA value, and the more likely a single phase solid solution can be formed. Okay, let's see what their results look like. So left hand side is the EFA calculations, and for example, for this material type compounds, the enthalpy distribution are relatively narrow. Okay, and if you the inverse of the distribution of the width is the EFA value, which is relatively high. Okay, for the bottom compound, you can see that the enthalpy distribution for these 49 structures, they have a wider distributions and thereby a smaller EFA value. Okay, and right hand side are the corresponding experimental data on X-ray diffraction peaks for the corresponding materials. And one see in the type of materials, you see clean X-ray diffraction peaks, indicating the formation of single phase solid solution of these 5 metal high-entropy carbides. In the bottom materials, you see a lot of noisy peaks, indicate you form only a multiple phases, not a single phase solid solution. Okay. So then, and in the follow-up paper, 2020 MPG composition materials, the group also have used machine learning to predict this EFA value. Okay, so and they have achieved a pretty good. So here this vertical axis are predicted value. Horizontal axis is the actual value from density function theory calculation. Okay, and you can see they achieve a pretty good results between the theory and the prediction. Okay, so one important conclusion they get from this machine learning prediction is that they found that the EFA value forming single phase forming ability is kind of inversely proportional to the average ionic character of your compound. Okay, so this might be something interesting to explore further in the future to test experimentally if one can verify this. And if it is true, it can help us to quickly select the single phase hydrogen materials that are more likely to be synthesized. Okay, so there's also another question is if these results apply only to the high-entropy carbides. Okay, so therefore we then try to test the results by focusing on the 5 metal hexagonal high-entropy borides with the AlB2 crystal structures. Okay, in particular, we focus on this 9 group 4 to group 9 transition metal elements. Okay, so to be compatible with the stoichiometry, we need to consider a minimum of 15 atom DOCC structures. Okay, and there in the end there are 84 distinct structures. So for a given chemical composition, we'll compute the enthalpy for each 48 structures. And so in total, we have 126 compounds to consider, and we have utilized about 3 million CPU hours on state supercomputer to carry out the test. Okay, so we are in the middle of writing the manuscript for journal submissions. So here I just show some of the results, okay, out of the 126 compounds. So first of all, for the say molybdenum, niobium, tantalum, vanadium, tungsten B10 compounds, we have a theoretical EFA value very high, 247. Okay, and this I also show the corresponding X-ray diffraction pattern obtained by Professor Ketteridge's group at the UAB. And here you can see clean single XRD peaks indicative of the formation of single phase high-entropy materials. In the middle, for this chromium compound, EFA value is slightly lower, and you can see we start to have small noisy peaks, but overall it's still a single phase solid solution. Finally, for this bottom chromium compound, EFA value is very low. You see a lot of noisy peaks indicate the formation of only multiple phases. Okay, so this good agreement-based theory and experiment indicates that it's indeed this EFA is a promising descriptor for the synthesizability of high-entropy materials. Okay, and will be published in our paper soon. Okay. So another thing I want to mention is that it's possible to use this POCC method to compute the mechanical properties. Okay. So right hand side is another example from our theory experimental collaboration with Dr. Ketteridge's group. So here on the top are the histogram plot for the harness value for all the distinct POC structure for these two high entropy borides. Okay, and then we do a thermal average based on the temperature of synthesis. Okay, so the theory indicates that first of all, the HEB1 compound has slightly higher hardness than HEBO2 compound, and second, they both have hardness value close to 33 GPa and 31 GPa respectively, and both results actually agree very well with the experiments. Okay, so this shows that the method is still powerful. However, there are two drawbacks. First of all, that is you need to consider all possible structures. So-called this is not very convenient. Okay, so it'd be nice to if we can get the structures, get the results in only one single calculation. And second, here we have a minimum only one transition metal per unit cell for a specific kind of element. Okay, so it cannot we cannot discuss, for example, lattice mismatch effects or the clustering or short range correlation between different transition metals. Okay, so in that case, we need to have use different methods, and that's the based on the spatial quasi-random structures. Okay, this is a big supercells try to mimic an infinite random alloy. Okay, so it's important here to check SQS supercell of different size and the geometry to make sure your results are converged. Okay, so in this paper again, in collaboration with Briasto in Catherich's group, we have compute the hardness value for different SQS supercells. So here the small green balls are the boron atoms, and the big colored balls are the transition metals. Okay, and one can see that the results converge to roughly 33 GPa. And also already at 60 atom SQS cell, the results are already pretty decent. Okay, so we thereby using these results of 60 atom SQS cell, then to again go through all the 126 compounds from these 9 transition metals for our 5 metal hexagonal high entropy borides. Okay, so this is one of the crystal structures, and these are the results we got. So we computed the hardness shear modulus, bulk modulus for all 126 compounds. Okay, and again, these calculations are performed by my students, Luke Moore and Ethan Fox, and we are we are in the middle of finalizing the manuscript for journal submission. So another advantage of this SQS cell is that we now have additional crystal structure information that can help us to come up with better machine learning models. Okay, so in particular, with this theoretically relaxed crystal structures, we can now have information on the, for example, the distribution of the say boron nearest neighbor bonds in the in plane, or the metal boron nearest neighbor bonds, and some other distribution, for example, for the metal boron or metal boron, or even second neighbor out in the C-axis or in the AB plane. Okay, so we can use this information, for example, the range or the distribution, such as width of a Gaussian fit, as our machine learning features. Okay, so these are the results based on random forest models. Okay, we have tried similar gradient boosted trees and achieve a similar result. Okay, so let's just focus on these results on random forests. Okay, so here are on the top rows are the prediction for bulk, shear, and hardness values. Vertical axis are the DFT calculation, the ground truth. Horizontal are the machine learning predictions. Okay, so another way to gauge the performance of your model is look at the root mean square error. Okay, so this is basically the the average of the square in the prediction error, square root of the average square error. Okay. So we see that, for example, in the bulk and hardness value, we can achieve a root mean square error less than 5 GPa, and the for the shear modulus, we achieve a IMSE about 11 GPa, so they are already pretty decent. Okay. So on the bottom figures are similar machine learning models, but now with additional crystal structure information. Okay, so one way we have talked previously about Pearson correlation coefficients, this is the definition. to measure the linear relationship between two quantities. Okay, so another way to gauge the performance of model is just look at so-called coefficient of determination, R squared. Okay, so this is the square of the Pearson correlation coefficient. Okay. And you can see that when we compare the bottom and top, we have improved in the R2 score, both for the test set and the training set. Okay, so this indicates that indeed, when we have additional structural features, we can improve our machine learning model prediction, okay, which is kind of expected. And from the resulting machine learning model, we can also extract the so-called feature importance. Okay, so this tells us which features are affecting our resulting target mechanical properties. Okay, so I plot the important features for the bulk, shear, and the hardness values. I'm not going into detail into each of the features. Okay, but I want to point out that what we have found interestingly is that, for example, in the bulk modulus model, if you look at the metal-metal boron-boron second neighbor distribution sigma, they have a negative correlation with the bulk modulus. Similarly, in the shear modulus model, if you look at the metal-boron bond distribution, then it has a negative correlation with the shear modulus. And similarly, if you look at the range of the metal-boron bonds in the distribution, they have negative correlation with the hardness value. Okay, so this indicates that lattice mismatch has effect on the mechanical properties, and they are negatively correlated with the results. Okay, so it'd be interesting, important feature, experimental and theory tests to check additional again these results. Okay, and we are about to finalize corresponding paper for journal submission. Okay, so in the last 5 minutes, I want to conclude my talk with some future research directions. So eventually, we want to model the high temperature, high pressure properties of these high entropy materials for extreme environment applications. Okay, so this I show the corresponding pressure, volume, temperature curves from Dr. Cicely Wang from Professor Yogi Shibara's group at the UAB. Okay, so you see this material, they are very stable, remain intact up to very high temperature and high pressure. Okay. So the modeling this PVD curve high entropy material will be unchallenged. Okay, so in the literature, a lot of people have utilized so-called quasi-harmonic approximation to simulate these finite temperature PVD curves. Okay, so this is a paper from our series experimental collaboration with Professor Barbara's group. Okay, on OSMIAN2 OS2B3. So this color balls are experimental data, and the solid lines are our theory calculations based on AM05 DFT functional with quasi-harmonic approximations. So in these approximations, the volume is allowed to change as a function of temperature, but we assume that a harmonic approximation for the phonon modes remain valid. Okay. However, we know these high entropy materials, their structure are stabilized by entropy effects at high temperature. Okay, so if you look at just the entropy terms, quite often these structures they are dynamically unstable. Okay, this means that their phonon modes have imaginary mode, have negative energies. This means that if you use a quasi-harmonic approximation, it becomes a problem. Okay, so the solution is to do ab initio molecular dynamics. Okay, so here I'm showing the corresponding calculations from my student Luke Moore. So in molecular dynamics, basically we update the trajectory of the particles based on the forces from DFT calculations. Okay, so these thereby very time consuming. It can be accurate. So these are results from 60 atom S-squared supercell for the volume versus pressure at roughly 300 Kelvin. So it's has a good agreement with the corresponding experiment within about 2% error. So the major challenge is that we are limited to about 100 atom supercell. It's accurate, but computationally very, very, very expensive. Okay. So once possible alternative is to consider classical molecular dynamics, where you update the particle trajectory based on classical force fields that are pre-trained. So this will enable very large scale calculations with over say 10,000 atoms or even larger. It's very fast, but its accuracy sometimes is not satisfactory. Okay, so now the trend is to consider the so-called machine learning force fields. Okay, so one of the most popular state-of-the-art research directions is which is able to obtain the best of both methods. Okay, so you will enable a large-scale simulations using classical MD, but meanwhile with the potential and the corresponding parameters to learn trend by ab initio molecular dynamics data. Okay, so this is the one of the direction we are now pursuing. So another important future research direction on machine learning is so-called the generative models. Okay, so just now we discussed about supervised learning, means that we have an input A, we want to predict some output B. Okay, for example, I give you a picture, you want to predict whether it's a dog or cat. Okay, so this is done by using so-called discriminative model, where we'll try to draw decision boundary on the feature space and make labels on the target data. Right? Another type of machine learning model is called the generative model. Okay, in this case, the model actually learned how data are distributed on the feature space. Okay, and once the model is learned, you can now sample a point in the latent space and to come up with pictures that mimic the real world data. For example, a cat mimics real world cat picture. Okay, in the paper published last year from my group, we have provided on Nature Computational Science, we have provided a mini review to talk about the usage of generative models for crystal structure prediction. Okay, so typical machine learning task is you start from crystal structures and you do a forward property mapping with a supervised learning to predict its property. Okay, so in the future we want to use generative model to start from a desired property space and perform an inverse materials design to create the corresponding crystal structure needed for that functionality. Okay, so as we review in the so there are popular generative models like variational autoencoder or generative adversarial network. Okay, so I'm not going into details in this talk. Okay, you can check for the detail in this paper. Okay, so but these are popular generative models that have already been applied to generate plausible crystal structures, okay, to facilitate our crystal structure prediction. And in fact, nowadays people have even used a large language model, for example, like ChatGPT, to create structures. Okay, so these are actually crystal structures generated from large language models shown in this reference. That's another review from Microsoft on using large language model for scientific discovery. Okay, so this in the future this would be a promising method to generate structures with design functionalities. Okay, and this structure can also help speed up the evolutionary structure searches by serving as the seed of parent structures. Okay, so with that, I would like to conclude my talk. So we have introduced supervised learning and applied that to discover new BCN and the BNO superhard materials with additional evolutionary searches and active machine learning. We also discussed about high entropy ceramics, especially modeling their synthesizability using the entropy forming ability descriptor, and model the machine learning property with SQL supercells and and machine learning models on the lattice mismatch effects. Okay, and for future research directions, we are pursuing finite temperature simulations with machine learning force fields trained on additional quantum molecular dynamics data. And also generative models will become promising for future crystal structure generation. Okay, so here I'm listing all the references from our theory experimental collaboration at UAB on these related topics. So including two manuscripts under preparation on simulating the mechanical properties and entropy forming ability for high entropy hexagonal borides. And so this work are supported in part by the U.S. Department of Energy and in part by the National Science Foundation. And we also want to acknowledge the fact that all the calculations are performed on the DOE-funded NERSC supercomputers and also the Frontera supercomputer funded by NSF. Okay, so with that, I will stop here and thank you very much for your attention. Bye.